Welcome to Electronics Pariksha channel. We'll solve some more problems of diode circuits of log electronics. Today we have nearly 12 problems which appeared in previous examinations and very important models. These questions appeared in Indian Engineering Services IES examination, and these are some of the important questions which appeared in IES as well as other previous central government examinations, state government examinations also. The questions related to diode circuits, clampers, clippers, and various rectifiers, Zener diode and all. So today we'll solve all these problems in great detail. Okay. Now let's come into the first question. You see, there are two questions. Both are related to each other. So that's why we'll solve these two questions together. So the first question, if you see, the use of rectifier filter in a capacitor circuit gives a satisfactory performance only when current is high, voltage is high, current is low, and voltage is low. Okay. This is the first question. And second question is, consider the following rectifier circuits: half wave rectifier without filter, full wave rectifier without filter, full wave rectifier with series inductance filter, and a full wave rectifier with a capacitance filter. He's asking the sequence of these rectifiers in decreasing order of ripple factor is. So we have to find out the ripple factor of these four things, and we have to put them in decreasing order. Okay. Okay. Now let's see. We'll see the filters. We have two types of filters, basic filters. One is capacitor filter. The other one is inductance filter. Okay, series inductance filter. This is also called as. We'll just see the comparison of these two filters. Okay. First, coming to ripple factor of these two filters varies. The ripple factor for capacitor filter is 1 divided by 4 root 3 FCRL. Okay, C is the capacitance, RL is the load resistance, whereas F is the frequency of the input signal. So this is the ripple factor of capacitor filter. The ripple factor of inductance filter is RL divided by 3 root 2 omega L. Omega is nothing but 2 by F. Okay, this is the ripple factor formula. Now, if you see the time constant for capacitor filter is tau is equals to RC, whereas R is nothing but RL, C is the capacitor that is attached. Whereas for inductance, it is omega L by RL. RL is nothing but load resistance, L is the inductance. Now, if you observe carefully, the filters, what they do basically. See, this is a rectifier. This is the rectifier circuit, and this is given to the filters. Either it can be a series filter as well as a capacitor filter. The output of the rectifier is pulsating DC, and filters usually charge and discharge. Filters usually what happens? They will charge and discharge like this. For example, it will be charged to peak value. The filters charge to peak value, and from this point onwards, they'll try to discharge. And again, they'll charge and discharge. So the output is nothing but this green color graph. That is nothing but a filtered output. Now, the time taken for the filter to discharge from this point to this point is time constant tau. So the time constant should be very, very high. If the time constant is high, the discharging of this filter will be the DC. The level of discharging will be very less. If time constant is very low, this is for high time constant. If tau is high. If time constant is very small, what happens is the discharging levels will be very, very, very high. Suppose the capacitor charges to this point and it will discharge to the deeper level. Again charging and discharging to the deeper level. This is because if time constant is less. Okay, so usually for the filters, the time constant will be very, very high. Time constant is the time taken by the capacitor to discharge from higher level, maximum level to certain level. So to reduce the ripples, ripples in the filtered output, usually time constant should be high. That is preferable. So if you look at this formula, tau is equals to RLC. To keep the time constant high, we have to increase the capacitor value as well as resistance value. If you keep this resistance and capacitor higher values, tau will increase. So when you keep when you increase RL, the current flowing through the filter circuit, what happens? It will be low. So current is obviously low. So capacitor filters are used for low current loads. This is the answer. So capacitor filters are basically used for low current loads. So the answer for the first question is the use of rectifier filter in capacitor circuit gives satisfactory performance only when current is low. Answer is option B. Now, similarly, if you look at this, the series inductance filter. To keep tau high, the resistance value, load resistance value should be low. So if the load resistance is low in case of series inductance filter, current will basically increase. So series inductance filters are used for high current loads. High current loads. Okay, this is for understanding. Now we'll see the ripple factor. The ripple factor for the consider following request. Second question, if you see the half wave rectifier without filter, it has got the ripple factor of 1.21, whereas a full wave rectifier it is 0.48. Full wave rectifier with the series inductance filter. Usually, what happens? The series when you use the series inductance filter, the resistance is usually low. The output voltage, as the resistance is low, current will increase, but the output voltage VL or V average, if you see overall, it will reduce because of the lower resistances. So output will be filtered output, but the average output, the average voltage at the output side of inductance filter is lesser than average voltage of capacitor filter. This makes the difference. This makes the ripple factor of inductance filter lesser than ripple factor of capacitance filter. Ripple factor of the full wave rectifier with capacitance filter. Okay, the average output of the full wave rectifier with the series inductance will be lesser than the average output voltage of the full wave rectifier with capacitor filter. That's why the ripple factor also comes down for the inductance filter. This is better than full wave rectifier without filter, less than full wave rectifier with capacitor filter. Okay, now if you order them, if you see them in the decreasing order, first comes half wave rectifier, second comes full wave rectifier, third comes full wave rectifier with inductance filter, fourth comes full wave rectifier with capacitance filter. So answer is option A. We'll see. Like the video, share the video, and subscribe to the channel for better content and more videos. Next question. The piecewise linear VI characteristics of a diode is shown in the figure. Actually, the figure is not given. I draw the figure. This is a figure. This is a piecewise VI characteristics. This is current I and this is voltage V. Here, the beginning voltage is 2 volts and upper voltage is 4 volts. And for 2 volts, the current is 14 milliamps. And for 4 volts, it is 34 milliamps. This is the graph given in the question. When the supplied voltage is 6 volts, if supplied voltage increases to 6 volts, what is the current? He is asking. So we'll solve this with the basic mathematics. Slope, if you take the slope formula, slope of VI characteristics, if you see, slope M is equals to I2 minus I1 divided by V2 minus V1, which is equals to 34 milliamps minus 14 milliamps divided by 4 minus 2, which is equals to 10 milliamps per volt. This is the slope. We need to find out current for 6 volts. So writing the equation I minus I2 is equals to slope V minus V2. So I minus I2 is nothing but 34 milliamps. Means you understood. Hope you understood. He's asking us to find out the current here at this point. 6 volts means what is the current? So this is I actually. This point is I. So I minus I2. This is I2. This is I1. This is V1 and this is V2. So I minus I2 is 34 milliamps and slope is 10 milliamps per volt. V minus V is nothing but 6 volts. It is given in the question itself. V2 is 4 volts. So by solving this, I is equals to 54 milliamps. Okay, that is the answer. We'll solve the next question. Consider the following statements. A clamper circuit adds or subtracts the DC voltage to or from the waveform. Yes, it adds or subtracts. Positive clampers adds, negative clamper will subtract. This is the positive clamper. There will be a capacitor in series with the input supply. If the diode is facing upwards, it is positive clamper. If the input voltage is sinusoidal waveform, the output will be like this. It is a positive clamper. Whereas the same capacitor, diode is facing downwards, then it is negative clamper. If input voltage is a sinusoidal waveform, the output waveform will be like this. The bias voltage is minus Vm here. In case of positive clamper, it is plus Vm. Okay. So here the waveform is clamped to plus Vm, clamped to plus Vm. Here it is clamped to minus Vm. This is the difference. So adds or subtracts the DC voltage to and from the waveform. That is correct. Does not change the shape of waveform. Yes, it does not change its shape of the waveform. Amplifies the waveform. No. Amplification is different. Shifting is different. I will tell you. Here, amplification means the sinusoidal waveform with suppose 2 volts. This is the example. 2 volts and minus 2 volts is there. If this is converted into 4 to 4 volts, positive peak is 4 volts and negative peak is also 4 volts. But the bias remains same. This is 0 volt and this is the bias of the input waveform is also 0 volt. This is called amplification. Whereas here in case of clamper, you are shifting the waveform. The bias is shifted to plus Vm or minus Vm based on the clamper, and the peak to peak voltage will remain same. Peak to peak voltage will remain same. That is 2 volts, sorry, 4 volts and 0 volts. That is plus 2 volts, minus 2 volts, like that. So amplification is different and clamping is different. So it doesn't do it doesn't amplify the waveform. It just shifts the waveform. So answer is option A, 1 and 2. Now we'll see the next question. A 24 volt 600 milliwatts Zener diode is used for providing a 24 volt stabilized supply. So the output voltage is 24 volt, and he's telling the Zener voltage is also 24 volt. Okay. Now assume the proper Zener action, a minimum of 10 milliamps must flow. So 10 milliamps is the minimum current that is supposed to flow through Zener diode. So that is nothing but IZ minimum. He is giving IZ minimum is 10 milliamps. That is the minimum current to flow through Zener diode. What is the series resistance and maximum value of the load current? So he's asking for series resistance and what is the maximum value for maximum load current? Okay, IL max. Now we'll see this. So we have two parts here. One is IS, the series current. Series current is equals to IZ plus IL. So here the variable parameters are load current and Zener current. If load current increases, Zener current reduces. If load current reduces, Zener current increases. And IS mostly remains constant because input voltage is constant. So now we'll take two cases. In case 1, we'll take IS is equals to IZ max. So Zener current is maximum plus load current is minimum, IL minimum. This is first case. Second case is 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 equals to IZ minimum plus load current is maximum, IL max. So both will contribute to each other, keeping the IS constant here. That is a concept of Zener diode action. So now here if you see IZ maximum, how to find out IZ maximum? IZ maximum is nothing but the power dissipation of Zener diode divided by Zener voltage. So the power dissipation is 600 milliwatts divided by VZ. VZ is 24 volts. So the IZ maximum is 25 milliamps. It comes around 25 milliamps. Okay, that is the maximum Zener current. So when Zener current is maximum, the load current minimum will be approximated to 0 milliamps. Why? Because here, if the Zener current increases drastically, load current is almost 0. Means here load resistance is variable. When this goes to infinite, RL is equal to infinite, IL is equal to 0. So the whole current flows through Zener diode as Zener current. So IS is equals to IZ maximum and the load current is 0. If you substitute here, IS is equals to 25 milliamps. The series current is equals to 25 milliamps. Okay. Now here, if you see the series current IS, how it can be written? It can be written as input voltage Vi minus Vz divided by resistance R is equals to series current IS is equals to 25 milliamps. So what is the input voltage? Input voltage is 32 volts. Zener voltage is 24 divided by R is equals to 25 milliamps. This is the equation we have. So from this, the resistance R is equals to how much it will be? 8 divided by 25 milliamps. So the resistance will be 320 ohms. Okay, this is the resistance, series resistance value. Now coming to the second section here, the series current IS can also be written as IZ minimum plus IL maximum, load current maximum. So IS is already known, 25 milliamps. IZ minimum is 10 milliamps from the question itself, plus IL maximum is means maximum load current. The maximum load current will be equal to 15 milliamps. Okay, so the answer is now resistance is 320, load current maximum is 15. Answer is option D. We'll see the next question. If the input voltage AC is a 10 volt RMS, the maximum voltage that will appear across the diode of half wave rectifier with capacitor input filter is. See, this is a half wave rectifier. It has got only single diode and a resistor RL. So this is connected across the capacitor filter. So capacitor C. So input voltage is 10 volt RMS. This is a 10 volt RMS. The maximum voltage that will appear across the diode of the half wave rectifier means when input voltage is sinusoidal waveform, when it is in reverse biased, when the diode is reverse biased, what is the maximum voltage across it? That is nothing but PIV, peak inverse voltage. The peak inverse voltage for the diode is VM, maximum input voltage. So here PIV is equals to V maximum. What is V maximum? It is nothing but VRMS multiplied by root 2. So 10 volts multiplied by root 2 is nothing but 14.14 volts. The answer is option B. For the next question, for the input of Vs is equals to 5 sine omega t, assuming ideal diode, circuit shown in the figure will behave as a. See, this is basically a clamper circuit. Okay, this is nothing but a clamper circuit. Which type of clamper it is? It is a negative clamper because diode is facing downwards. Diode is facing downwards, so it's a negative clamper. This is the output. Okay, so you have applied a sinusoidal voltage here of 5 volts. Peak voltage. Peak voltage is 5 volts. Okay, the output here will be, see, this is no bias. I am taking zero bias here. What is the output voltage? The output voltage is like this. It is a negative clamper. So minus VM, minus VM in the sense here it is 5 volts. In case of this, it is 5 volts. Minus 5 volts. So usually the waveform will appear like this. Minus 5 volts, and this is minus 10 volts. So it is clamped to minus 5 volt. Input waveform is clamped to minus 5 volt. This is with zero bias. Now he is applying a negative bias. Here he is applying a negative bias, that is minus 2 volt. So when you apply a negative bias here, what happens to output waveform with the negative bias? Here it will be, usually it is clamped to minus 5 volt. With the negative bias it will be clamped to minus 7 volt. Usually it is clamped to minus 5 volt. So you have added a minus 2 volts. So it will be clamped to minus 7 volt. 5 plus 2, it is 7 volt. Okay. So draw the diagram. Minus 5, minus 7 plus 5. So here the positive peak is at minus 2 volt. Minus 7, minus 5. So the negative peak is minus 12. Okay. So this is the waveform. So it will be clamped to, it is a clamper circuit. It is a clamper circuit and it is clamped to minus 7 volt. Sorry, here clamped to minus 2 volts because the 2 volts is a peak voltage. So answer is option B. It will be clamped to minus 2 volts. We'll see the next question. Now similar question if you extend, I would like to extend. If you apply the positive bias, with the positive bias what happens? Assume the positive bias is 2 volts. You have applied plus 2 volts instead of minus 2 volts. What will happen to the output waveform? Try to analyze. This is the diode and you have applied positive 2 volts. What will happen? The usual waveform is this. This is the usual waveform. So this waveform will further shift upwards by plus 2 volts. That's it. That is the answer. We'll see here. This is a zero bias. Usually it should shift to minus 5 volt, but you have added plus 2 volts. So it will be shifted to minus 3 volt, which is nothing but minus 5 plus 2, minus 3 volt. So minus 3 volt plus 5, that is nothing but plus 2. Minus 3 volt minus 5, that is nothing but minus 8. So the output waveform will be like this. Minus 8 and this is plus 2 volt. Hope you understood the logic here. Okay, if it is negative bias, the waveform goes further negative. If it is positive bias, the waveform will move positive towards positive. But this is the regular case with zero bias. You have to compare with zero bias only. First, it will shift to zero. First, it will act like a normal clapper, and then you have to move upwards or downward direction based on the applied bias voltage. We'll see the next question. Like the video, share the video, and subscribe to the channel for better content and more videos. In the circuit shown figure, E1 is 2 volts, E2 is 5 volts, and E3 is 1 volt. Capital E is 2 volts. Which one of the diodes will be conducting? So here in the circuit, he has given E1 as 2 volt and E2 as 5 volts, E3 as 1 volt. So there are three diodes. This is D3 and this is D2 and there is D1. These three diodes are connected to a common terminal resistance and connected to plus 2 volts. Okay, so this is basically the circuit. Now if you see, first we have to tell which diode is conducting, first we have to find out the potential difference across each diode. If you see the potential difference across D1, a positive terminal is connected to 2 volts, negative terminal is connected to 2 volts. So basically the potential difference is 0 volts. Similarly for D2, if you see, the potential difference here is 3 volts, 5 minus 2, 3 volts. For D1, the potential difference is 1 minus 2, minus 1 volt. Okay, so you can see from the diagram it can be told D1 and D3 will not be conducting. They do not conduct because those are reverse biased. So D2 is in forward biased. It will start conducting. D2 conducts. Okay, so current flows from 5 volt through D2 to the resistor R and 2 volts. So current flows in this direction. Only D2 will be conducting. Answer is option C. Only D2 will be conducting. So the output voltage is nothing but 5 volts here. The output voltage will be 5 volts because entire 5 volts appear here. As the T2 is conducting, entire 5 volts appear here. So the output voltage is nothing but 5 volts. We'll see the next question. In order to rectify the sinusoidal signals of minimum of millivolt range less than 0.6, which will be used? So bridge rectifier using diodes can be deployed? No, because here in bridge rectifier, two diodes D1, two diodes will be conducting at the same time. So the voltage drop across diode is 2 VD. That is 2 into minimum 0.7. That is 1.4 volts. Itself is a voltage drop. He is asking less than 6 volts is less than 0.6 volts is the input voltage. So it is not possible. Full wave rectifier? No. A diode can be inserted in the feedback loop of operational amplifier. Yes, this is correct. We have to use operational amplifiers. An op-amp is also called as micro amplifier because it will amplify the microvolts to millivolts, 2 volts. Okay, this is plus and this is min. Input will be in the form of microvolts. Mostly, it will be converting the microvolts to millivolt range to volts level. Okay, the output will be in volts. Output will be in volts. Suppose 2 microvolts is there. Output will be approximately in volts, 2 microvolt or 2 millivolt. It can be converted into volt. So when it is converted into volts, it will be amplified by the operational amplifier. And as this is in the range of volts, not in the decimals, this can be easily rectified by placing the diode in the output loop, feedback loop. Okay, that is the concept. This is the output feedback loop. This is the load resistance RL. So operational amplifiers to be inserted. Operational amplifier will be used with a diode in the feedback loop. This answer is option C. Like the video, share the video, and subscribe to the channel for better content and more videos. The input voltage of the Zener diode varies from 20 volt to 30 volts. The load current varies from 10 milliamps to 15 milliamps. If the Zener voltage is 5 volt, the value of series resistor is. So the circuit is like this. This is a series resistance, and there is a Zener diode here. He is telling the load current will vary. This is a load resistance RL. Okay, load current is varying from 10 milliamps to 15 milliamps. Means IL ranges from 10 milliamps to 15 milliamps. The maximum load current is 15. The minimum load current is 10. Input voltage varies from 20 volts to 30 volts. Zener voltage is 5 volts. So now let's find out the resistance R. Resistance, series resistance RS is given with input voltage should be minimum. V in minimum minus Vz divided by current I. Always series resistance is calculated with V in minimum. If input voltage is varying, if input voltage is fixed, you have to consider that fixed value. If input voltage is varying, you have to consider V in minimum value. Okay, V in minimum minus Vz divided by Is. Now we know V in minimum, we know Vz. We do not know what is current I. So we'll calculate current I. Current I, we have two formulas again. Current I can be given as Iz minimum plus IL maximum. Minimum Zener current plus maximum load current, or maximum Zener current plus minimum load current. Okay, these are the two formulas we have. To use this formula, we should know Iz maximum. How Iz maximum is calculated? With power dissipation, Pz. Okay, if power dissipation of the Zener diode is given in the question, use this formula. If it is not given in the question, don't use this formula. Okay, so in our question, the power dissipation of the Zener diode is not given. So we have to use this formula. I is equals to Iz minimum plus IL maximum. We'll use that. What is the minimum Zener current? That is not given here. And it is not specifically mentioned that the Zener minimum current, knee current of the Zener diode is this much. So when it is not specifically mentioned, you have to assume Iz minimum as 0. So I'm assuming it as 0 plus IL maximum, it is given as 15 milliamps. So current I is equals to 15 milliamps. Now substitute this value here. Series resistance V in minimum is 20 volts minus Zener voltage is 5 volts divided by I 15 milliamps. You will get a series resistance as 1 kilo ohm. So answer is option A. Now we'll see the next question. For the circuit given in the figure below, assuming ideal diode is ideal, the output waveform is, this is basically a clipper circuit. This is basically nothing but clipper circuit R. This is the diode which conducts during the positive half cycle, negative half cycle it does not conduct. So output will have the negative half cycles here. Output will have negative half cycle. Okay, this is with zero bias. When there is no bias, zero bias. Zero bias in the sense there is no voltage applied here as a bias voltage. If you apply a bias voltage, now here the bias voltage of plus 5 volts is applied. With the positive bias, what happens? With the positive bias, what happens? See carefully, observe this carefully. This is the input voltage. Okay, this is the input voltage of 10 volts and minus 10 volts. In the question, it is given as 10 volts is the maximum peak value. So the usual waveform is this one. Only negative half cycle should exist. So negative half cycle will come into picture. He has given the positive 5 volts as a bias voltage. So what happens is here some portion from the positive half cycle also will appear in the output voltage. So this is the positive 5 volt breakdown. So even that 5 volts will come into the picture. Waveform will contain the portion of positive half cycle also. So this is 5 volt. This is 5 volt. Output waveform will have some portion from the positive half cycle also. This is 5 volt and this is minus 10 volt. This is the output waveform with positive bias. If negative bias is given for the same circuit, if the negative bias is given, with the negative bias we'll see. Means assume minus 5 volt is given as a bias voltage. What happens to the output? The portion of negative half cycle, earlier this is the original output. Some portion from the negative half cycle also will be removed. So output will be like this. This is with negative bias. This is minus 5 volt, and here it will be minus 10 volt. So you should be careful while answering the question. What is the bias voltage given here? Whether it is a positive bias or negative bias, you have to see. Positive bias means add the positive portion to the existing waveform. Negative bias means remove that remove the existing portion and give the output. So now the answer will be here. Actually, here the option is not given. The C and D option are not covered. So the answer is here, this one, this waveform, because the positive bias is given. This is the output voltage. We'll see the next question. If you see the diagram, he's asking us to find out R1 resistance. Here in the question, he's asking us to find out R1. Find R1 resistance. So series resistance. This is nothing but a series resistance. Rs equal to Rs. We'll try to find out. Here, current I can be given as greater than or is equal to Zener current plus load current. I is nothing but a series current. This current. A series current IS is flowing here, which is nothing but I. The series current IS should be greater than or equal to IZ plus IL, Zener current plus load current. The same current splits here. It will split into Zener current and it will split into load current. So IS greater than or equal to IZ plus IL. Whereas IL can be written as the output voltage divided by load resistance. Here load resistance is R2. And IS, that is series current, can be given as V input voltage minus V Zener voltage divided by R1. R1 is nothing but series resistance in our case. So substituting these values, you will get V in minus Vz divided by R1 should be greater than or equal to Zener current Iz plus load current V output divided by R2. Here the Zener current is also given as Zener current Iz is equal to 10 milliamps. That is given in the question itself. So if you substitute that V in minus Vz divided by R1 greater than or equal to 10 milliamps plus V naught by R2, we will get this 10 milliamps we can write as 0.01, and we will get R1 less than or equal to V in minus V naught divided by minus V naught multiplied by R2 divided by 0.01 R2 plus V naught. So the answer is here is option C. Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.